from Nitspor Institute on MHV rules and pure Yang mills.
Okay, yeah, thanks a lot for the invitation to be here, also the opportunity to present this work. So this is actually not the most recent thing I've done, but I thought it might be more interesting for the audience here. And it's some work that I did back in April with people from Queen Mary, where I used to be until last month. And there is some ongoing work which I'm going to discuss very briefly at the end. So I like to start at the beginning, although people don't really think of this way anymore. So the beginning was, well, as far as I'm concerned, is the paper by Witten in 2003, late 2003, where he described a new, or he proposed a new gauge theory string duality, which relates n equals 4 Yang mills, but this time in a perturbative expansion, to something he called the instant expansion of the topological B model on CP3/4. I'm not going to spend much time on this because it's not relevant to the rest of my talk, but this is just to remind people where things more or less started. So this CP3/4, as we heard also last week, is super twistor space. It's a 6-dimensional bosonic manifold with super coordinates attached to it. And the way this correspondence works is that there's this mapping called the Penrose transform, which relates forms on CP3 with a given homogeneity to massless fields of a given helicity on normal Minkowski space, which we're interested in. So that's how these theories defined on different space-time dimensions can actually be argued to be dual to each other. So to see how Witten arrived at this conjecture and to set up some formulas for later, let me discuss the spinor helicity formalism just very briefly. It's been known for a while, since the 80s or so, that gauge theory amplitudes, if you express them not in terms of the usual Feynman diagram approach with covariant helicity sort of vectors at the end as external states, but rather in terms of fixed helicity external states, appear much simpler. And the way we do that is for massless particles, which is all I'm going to talk about in this talk. First, write the momentum as a 2x2 matrix using this standard the sigma matrices, and then the fact that it's massless, so p squared is 0, means that on shell you can split it into a product of spinors, one holomorphic, one antiholomorphic, which you can associate with positive and negative helicity. And then you can define this notation, which I'll also be using quite a bit. This is the holomorphic product of the two spinors, and this is the antiholomorphic product. So these are just normal two-component spinors. So the result, if you write amplitudes in this way, and I'm going to be talking about amplitudes for this talk, is that if you have 0 or 1 negative helistic gluons, and all the rest of the gluons positive, and this can be sort of this one is trivial to see. I'll discuss this later, and this you have to do some summation over channels. But anyway, the result is that the amplitudes vanish. So the only non-trivial amplitude starts from 2 negative helicities, and it's given, which is called maximum helicity violating, and it's given by this formula, the Park-Taylor formula, again known since the 80s. And Witten sort of got motivated by the fact that this actually is a very simple answer. And for a calculation that even though this is tree level, can easily, I mean, if you get to large order, can easily take thousands, if not millions, of Feynman diagrams to actually, if you wanted to really do the calculation in an honest way. So he was trying to find an underlying reason for this simplicity. And he came up, well, or the way he started thinking about it was, well, amplitudes, as I said, I just said now you can describe them by these spinors, holomorphic and antiholomorphic spinors, but take this antiholomorphic one and do a Fourier transform, basically this and another conjugate relation for for mu, and map it from the normal spinor to something else, a different kind of spinor, which defines a coordinate on twistor space. So twistor space, or more precisely projective twistor space, is the manifold derived by this. So you take these two things as coordinates. These are 4 complex numbers. There is an obvious symmetry where, because remember the momentum was lambda lambda tilde, so you can always rescale lambda and lambda tilde oppositely by a complex number. And that maps to the fact that lambda and mu are rescaled the same way, since mu is related to lambda tilde. So you get a 3-dimensional manifold, 3 complex dimensional manifold. And for CP3/4, all you need to do is add fermionic directions. So the main result here is which has been discussed by Penrose originally, is this incidence relation, which very roughly maps points in twistor space. So if you fix points, and this means you fix a point like mu and lambda to have a set value, and then you try to solve this equation for x. This is actually wrong. It's not a null cone. It's some particular null planes in twistor space. And you can have two varieties of null planes in normal space-time. So it tells you something about the causal structure of space-time. And it works in another way. You can see it the other way. Fix this, fix a point in space-time. Then this you can just read off as an equation defining a line in twistor space. So this was a fundamental thing that was well known. And what Witten did was he took these amplitudes I discussed, I showed before, so this Park-Taylor form, for instance, and mapped it to twistor space by using just this simple mapping. And he came up with a conjecture that for n equals 4 Young-Mills, scattering amplitudes are supported on particular curves in twistor space. So they actually have a meaning when you take an amplitude, you map it to twistor space in this way, and it actually has some geometrical meaning. And the meaning was it's supported on a curve like this, where d is the degree of the curve, q is the number of negative holistic gluons in the original amplitude, so that would be 2 if it was an MHV amplitude, 3 if it's next to MHV amplitude, and so on. And L is the number of loops of the amplitude, so if it's tree level or loop level, and so on. Now, people don't really think much of this anymore. This is more a review of the original picture that people had. But in particular, this led to a very nice development, because one can think of MHV tree-level amplitudes, which have q equals 2 and L is 0 because they're tree-level. That gives you just degree 1 curves and 0, 0 if you follow this. So they are actually supported on complex lines in twistor space, which you can draw two ways. Either you think of a CP1 embedded in CP3 like that, or you can think of it in a complexified sense, where just a line, a complex line. But this is kind of confusing because it kind of implies that there's an ordering which is not really there, because it's really a CP1. And now you remember from this incidence relation from last transparency that the Penrose transform maps these kinds of lines precisely to points in Minkowski space. So the next development here was done by Kaczmarov, Zwerchek, and Witten, which said, well, what then, if these MHV amplitudes are actually, in a sense, related to points in twistor space, on Minkowski space, then maybe we can think of these amplitudes really as supported as points, so really as vertices. So then, why don't we construct tree-level non-MHV amplitudes by trying to joining up these vertices appropriately? And this is kind of the twistor space picture, and this is more or less the space-time picture you have. So in this picture, so you've upgraded your MHV amplitudes to actual vertices. So this is what is it? A 5-point MHV vertex. It's MHV because it has 2 negative helicities, and all the rest are positive. And it's mapped by a propagator, which they took to be just 1 over p squared. It's combined with some other vertex, and it gives you a next to MHV amplitude. See, it has 3 negative helicities. So that's the proposal. And although I'm not really giving much motivation in this talk, but one of the motivations for this is that you actually can simplify the calculation of amplitudes with many particles by a great extent by applying these methods. And it was soon found out that supersymmetry is not even necessary for this. This was in the context of n equals 4, but you can more or less apply the same rules for non-supersymmetric theories. So even for QCD, and especially for the massless case, everything is quite nice. Now, before I go on, there's a short technical, little bit more technical transparency, which is, well, I was saying that we take these MHV amplitudes and we're instructed to think of them as vertices. So then we have to connect them to other vertices and so on. So we have to know them off shell. So the question is, how are they defined? Because these amplitudes were defined in terms of spinors, these holomorphic and anti-holomorphic products. But if you take the momentum to be off shell, then you cannot actually factorize into spinors anymore. So what spinors are we talking about? So to sort of circumvent this problem, CSW just decided to use an arbitrary reference spinor, like that. It's an anti-holomorphic spinor. You take the momentum, which is not actually on shell anymore, because now it can be arbitrary, and you define the holomorphic spinor like this. So you introduce an arbitrary reference spinor into the game. And another way of seeing the same thing is that if this is your momentum, L, you can always write it as some null momentum, L squared, plus something related to eta, where eta is now an arbitrary null vector. So eta, which is just a product of two particular spinors. And then you can argue that the momenta that you want. So these lambdas are defined by factorizing this L and not the big one, which is not factorizable because it's not on shell. But of course, what you have to do if you introduce these arbitrary spinners or vectors in the game is that you actually have to show covariance at the end. You have to show that nothing depends on the choice of this. So this was the situation at 3 level. Now at 1 loop, things didn't seem to work that well in the beginning because at least on the two-star space side, it's still not very well understood. And one of the main problems is that everything was defined in terms of the B model, and if you really want to believe Witten's original two-star picture, and that was the open B model. But then if you start trying to do 1 loop stuff, then you also get the closed B model states propagating and mixing with your open string calculation. So then you get, and that's mapped in spacetime to conformal supergravity. So you get a picture where actually, if you want to think of this at loop level, it's not really Young-Mills anymore. It's Young-Mills coupled to conformal supergravity. And there were many other issues also, which made this picture a bit not very optimistic. But actually, if one just goes ahead and does the calculation in space-time, so with the calculation, I mean, we'll take 2 MHV vertices, 3 level, and just combine them into a loop, which is what the group at Queen Mary did. They found out that you actually can reproduce once you define some things properly, like what is the measure that you're actually using to do the loop calculation. You can actually reproduce the 1 loop MHV amplitudes that were known from before. So actually, it does seem to work at loop level. And it has been extended. This was for n = 4, but you can do it for lower supersymmetric theories, and even for some non-supersymmetric theories, but you can't capture the full thing. And this is where I'm going. You can only capture the cut constructible parts of it. So these are parts of the amplitudes which have discontinuities, so basically, through using their cuts, you can reconstruct the whole amplitudes. But of course, there are amplitudes which are, say, rational. They don't have any cuts, so you cannot reproduce them using this method. So for supersymmetric theories, it has been shown that any amplitude that you want, even the rational parts, can be recovered through this because they're related in a unique way to the non-rational parts. But that's not the case for any non-supersymmetric theory. So here are some what's known in terms of proofs of these rules. So at 3 level, again, CSW showed covariance, so no eta dependence. They showed that the singularity structure is correct. Also, there's a nice proof by Riesager, who used what's known as the BCFW recursion relations. I'm not going to go into that, but it was a field theory proof also that these MHV rules work at 3 level. There's a Lagrangian approach, which will be the main focus of this talk. There's also another sort of way of thinking about these things in terms of two-star space actions. So there's a group in Oxford which started by lifting this whole business to two-star space, and then from their point of view, the difference between sort of the normal Lagrangian, sort of the Feynman, to get using Feynman rules, and a Lagrangian where you have this MHV rules, it's just a choice of gates. Because they're in 6 dimensions, they have much more gauge symmetry in a sense. So depending on how they fix their gauge, they can go from the normal space-time picture to this MHV picture. But that involves going to higher dimensions, and it's not so clear how everything works, especially at the quantum level. Now at 1 loop, again, the Queen Mary group showed that these properties hold. So amplitudes you construct, any amplitude that you construct by joining together MHV vertices, has covariance, has the right discontinuities, has the right soft and collinear limits. There's another technical requirement, which is the multi-particle limits, which was kind of too difficult. But more or less, people believe that for supersymmetric theories, everything is fine, and you can apply these MHV rules. At higher loops, nothing, as far as I know, is known. And also, there's no results, although I think there has been lots of work, especially in the beginning, on non-perturbative effects. So I mean, the goal here would be to say, well, can we actually use these MHV rules to describe everything we want to know about Young-Mills theory? So can we not forget about the usual Feynman diagrams based on a quarter trace F squared and use MHV rules instead? And at 3 level, you can do that. At 1 loop, for supersymmetric theories, you can do that. And at higher loops, or as far as non-perturbative effects are concerned, nobody really knows. Okay, so let me focus at the 1 loop problems. And in this talk, I'll be focusing at 1 loop from now on. So as I said, this procedure does not reproduce the rational parts of non-supersymmetric amplitude. And if you just focus on pure Yang-Mills theory, so this is pure non-supersymmetric, just Yang-Mills theory, there are amplitudes which you cannot even write down if you have MHV vertices. And an example is this so-called O plus amplitude. So this is an amplitude where I've drawn the helicities here. So you have all the incoming or outgoing, let's say, particles have positive helicity. And all the vertices here, if you see, are one negative, one positive, two positive. So they're a vertex which is anti-MHV. Remember, MHV vertices, the whole point of it was that you can have two negative and one positive. So you can do everything just using that vertex with two negative and, say, any number of positive. But here you see an amplitude which actually requires exactly the opposite. There's no way to construct this from MHV vertices. However, this is not zero. It's a known rational function. And it looks like that. It's been derived in this paper. So that's something that MHV rules definitely cannot reproduce the way they've been used so far. And also the single minus, where you flip one of these pluses and make it a minus, has the same kind of problems. It's also a finite amplitude, and you cannot reproduce it from MHV rules. So one of the original ideas that people had was, well, maybe we can actually think of, since we cannot reproduce it by MHV rules, let's put it in by hand. So let's extend this amplitude off shell like that, and think of it as a new vertex in the theory. And maybe that will be fine. So then we can have the MHV rules plus this new one-loop vertex in the theory, and maybe things will combine nicely. But the original the original extension that CSW did in a different paper didn't work. And one of the problems, of course, is that, well, okay, maybe it's hard to see, but in the original MHV Park-Taylor form, it was very easy to extend off shell. This is based on the trick that I mentioned with the reference spinner and so on. Here it's actually much more difficult because you have both holomorphic and anti-holomorphic spinners, which actually means that there's many ways to rewrite this amplitude, and they would be inequivalent if you extended them off shell. So it's actually very hard to figure out which is the best way to extend this amplitude off shell, even if you wanted to do it. So the naive extension that CSW picked didn't actually work.
So this formula is conjecture, or
No, this is based on actual calculation. Using they were using the unitarity approach.
it's good at one loop, and the tree level is also known.
For this so for tree level, it's up to 0. As I said at the beginning, everything with O plus or a single minus is 0 tree level, which explains why it's actually finite at one loop. There's no any way you cut it. There's nothing there. Everything will be single minus. So that's why there's not a vertex here. It's just a finite answer. But this is known. Yeah. So, and that's what we want to reproduce using the MHV rules. Okay, so that was about sort of the review of what was known. Now I'm going to discuss. Well, it's not a very recent anymore development. It's this so-called Mansfield transformation. It was developed by Paul Mansfield in Durham. And there's a very similar transformation which was independently done by Gorski and Rosley at around the same time. So technically I should be calling it the Gorski-Rosley-Mansfield transformation. But I'll stick to Mansfield because that's the presentation approach that I'm going to be using. So the idea of this is to prove the MHV rules. Another proof, let's say, of the MHV rules. But the technique is kind of different from previous ones in that, first of all, you start by considering Yang-Mills on the light cone. Which restricts you to only physical polarizations. And then you perform a canonical, in a way I'll explain, non-local field definition on your fields of light cone Yang-Mills. And the goal is that after the transformation, the Lagrangian becomes an infinite expansion, with every term being an MHV vertex. So this is telling you that you take normal Yang-Mills, transform it, and get an MHV Lagrangian, which by definition has to have an infinite number of vertices, each of which is MHV. So all of them will have two negative helicities and any number of positive helicities. Let me say just some notation. So Yang-Mills on the light cone. I'll be going to light cone coordinates like this, and I'll be fixing light cone gauge using a reference vector eta, okay, and a null vector. And now you can see immediately that if you take normal Yang-Mills, and I'm suppressing the traces here, but this is normal non-abelian Yang-Mills theory. If you take Yang-Mills, and you do this procedure, then you end up with something like that. And the important thing here is that, okay, first of all, you've killed off A minus, one of the components of the gauge field. The other component, A plus, appears only quadratically at most. And there are no time derivatives acting on it. Time is now taken to be x minus for us. Often people take x plus on the light cone, but we've taken x minus. And this means that we can actually integrate it out. It's non-local. There's a derivative in the denominator, but you can integrate it out. And you end up with a final Lagrangian, which depends only on the physical polarization. So AZ, which we associate with polarization plus, and AZ bar, which is polarization minus. The structure is very simple. After you do that, it looks like that. It has a kinetic term. It has two cubic terms, two different kinds of cubic terms, let's say, and the quartic term. And the structure is simply given by this. Now, the point that Mansfield noted is, well, is that, okay, this Lagrangian is nice, but it has a problem, which is that it contains this vertex which is not MHV. So if you think in terms of deriving MHV rules, well, of course, you know, this vertex is not MHV. That's one initial observation you can make. So what he thought of doing is actually eliminating it. And how did he do it? Well, let's do a field definition. So A is expressed in terms of the new fields B, and A bar is expressed in new fields, and it turns out to depend on B bar and on B. And the goal is that after the transformation, you want the kinetic and the plus plus minus term, so the vertex that is anti-MHV, if you want, to just combine into a purely kinetic term. So you basically, schematically, that's what you do. Propagator, the kinetic term plus this interaction term becomes just an interaction term after the transformation. That's the Mansfield transformation. Now, that just defines one equation on two variables, A and A bar. You want the second one. And the second one that he proposed to use is canonicality. So the canonicality basically meant that you don't want any Jacobian when you do the transformation. So you want the measure to be invariant, the Jacobian to be 1. And why is it called canonical? Because you can think of the conjugate momentum of A is proportional to A bar. That you have to look at the original Lagrangian to see this. So roughly dA bar, which is the original path integral measure, looks like dA conjugate momentum of A. And so if the transformation is canonical, then and up to issues related to this determinant, which you factor out from both sides. If you can ignore safely these issues, and he argued that you can, then if the transformation is canonical, then there is no Jacobian generated. And the canonicality condition explicitly looks something like this. But anyway, so you have two different conditions on your two fields. And what Mansfield showed is that if you require these two things, you can determine precisely this change of variables. And initially, as a power series, let's say. So you want A and A bar to be power series in B. A, remember, depends only on B. But A bar depends on B bar and on B also. And the crucial thing that follows from these requirements, which was not obvious in the beginning, but it follows from these requirements, is that A bar is always linear in B bar. So this transformation is always linear in B bar, but has an ever-increasing number of B's. And that means that now this was set up so that to kill the kinetic term plus the one vertex, but now I have to plug it into the remaining vertices of the theory, which were the other vertex plus the quartic. But since all of these already have two B's, and this A bar is always linear in B bar, then every other vertex that you get out of this will also have two B bars. So that's schematically what we've done. We've killed off these terms, we've got just the kinetic term, and then these terms, if you plug back in what the transformation is, in terms of the B fields, are an ever-growing expansion, but with just two negative helicities at each vertex. So this starts looking like an MHV Lagrangian. Now, because MHV, remember, meant that you always use vertices which have two negative helicities and a number of positive. Of course, that's not proof of it. You have to actually prove that the precise form of each one is an off-shell MHV amplitude. And Mansfield had some general arguments why that should work. And then, immediately after that, or very soon after that, there was a group in Southampton, et al. And Morris, which actually found a closed form for these coefficients. So remember, before it was just a polynomial. Now you can write it as explicitly as a power series in these with these new coefficients y or epsilon. So this is A expressed in terms of B's, A bar expressed in terms of B's and one B bar, which, because these are matrices, you have to sum over all permutations. And the actual coefficients that you can immediately derive from Mansfield's two requirements, I mean, killing the vertex and canonicality, are these ones. And they check, or explicitly really only at 5 point, but everybody believes that sort of the proof is correct, that this reproduces the MHV vertices. So if you plug these coefficients in the Lagrangian, and you sum up all the terms that come up, then each term is going to be an MHV vertex, and at 4 point, 5 point, and so on. Excuse me?
What's the reflection of the eta spinors?
Okay, I'm coming to that in a second. Actually, it's the next expanse. Okay, so as I asked, in the MHV rules you have typically, you needed to put an arbitrary spinor here, an arbitrary reference spinor. Either a spinor or a full null vector. But now we're on the light cone, so it's actually very natural to identify the spinor with the spinor that defines the light cone surface to begin with. So if you do that, and this is sort of one reason why the light cone is very closely related to an MHV kind of approach. First of all, because you have physical polarizations, which also MHV vertices are always physical. They either contain minus or plus helicities. But anyway, if you can do that, you can actually show that these brackets that we defined before in terms of spinors, so the holomorphic and anti-holomorphic one, can actually be constructed directly out of the light cone components of the momentum. So from now on, everything I'm going to say, these brackets are not made of spinors anymore. They are defined like this. And this is a very nice way to extend them off-shell. So this is a true on-shell and off-shell. It just contains momenta. There's no spinors anymore. So the formulas will look the same, but from now on, these brackets just mean this. Okay, is that clear? Okay, one of the obvious questions that people asked when this came out is why does it work? No, P minus is the conjugate of the time of x minus, so it did not appear. Yeah. Yeah, we've taken x minus to be the time direction. So, okay, why does this work? So, because somehow we're taking Yang-Mills theory, okay, on the light cone, and we're doing a sort of more or less arbitrary Fuller definition. And why do you expect it to give something nice and simple like the MHV rules? And one way of understanding this issue is that these two vertices, so the kinetic term plus this vertex, are a light conversion of self-dual Yang-Mills theory. So what Mansfield has really done is mapped self-dual Yang-Mills to a free theory. And this actually does make sense, although it might look that we're mapping an interacting theory to a free theory, but actually self-dual Yang-Mills being a classically integrable system is not really an interacting theory at tree level. So although you can write down Feynman diagrams, after summing over channels, all amplitudes vanish. And this is in normal Minkowski space. So it actually is consistent at tree level to map self-dual Yang-Mills theory to a free theory. So that's one way of understanding why we did not get something horrible coming out. Because we're actually taking a theory which is somehow simpler than we think, and we're mapping it to something extremely simple. But the problem is, of course, that at loop level, this stops happening anymore. Because in self-dual Yang-Mills, you can have one loop amplitudes which are non-zero. So it's not integrable at the loop level, at the one loop level. And and this amplitude that you can calculate is exactly the same as the O+ amplitude I mentioned before in full Yang-Mills theory. This is not obvious. You have to actually prove this, because now we're talking about self-dual Yang-Mills, but it's a result by Kangemi that the O+ amplitude, which is the only amplitude in self-dual Yang-Mills, is mapped or is equal to the O+ amplitude of full Yang-Mills, which of course has many more amplitudes. But so what Mansfield has done is illegal at one loop. And that maps the fact that we've lost these particular amplitudes, these O+. So, of course, I mean, so even if you restrict to this self-dual Yang-Mills sector of full Yang-Mills theory, you have to understand, if you want to go further, you have to understand what's wrong with Mansfield's approach. And for full Yang-Mills, there's more things to do apart from this amplitude. There's also the single minors, there's also rational terms in amplitude. So many problems at one loop are not really solved by the Mansfield transformation. So for supersymmetric theories, however, all this is not a problem, because this one loop amplitude that I mentioned actually vanishes if you sum over all species propagating in it. So this is really a problem for pure Yang-Mills theory. Any amount of supersymmetry, even n equals 1, is enough to make this 0. So all the previous proofs that I mentioned of MHV rules at one loop still work without having to invoke anything new. But the focus is on pure Yang-Mills. So I'm going to focus on this all plus amplitude. And for the moment, I'll be in the self-dual sector. So where could the missing amplitudes be? One way of thinking about this is through the equivalence theorem. So basically, this tells you that, well, although you don't expect, if you do a Filler definition, you don't expect correlation functions to be the same in the two theories. If you take a theory and you define it, you define your fields, obviously correlation functions will be different. And that's very schematically. If you have, depending on A, and you calculate correlation functions by taking derivatives with respect to sources. Now, if you go to a theory where you've taken care, so this is a multi-field, it's not necessarily only A, but if you take care that your Jacobian is 1, and you map S of A to S of B, but then here you're going to get some function A of B. And sort of the statement of the equivalence theorem is when can you safely replace A of B by just B, so that you can take correlation functions in the same way by taking derivatives with respect to B. And there are a few things that have to be, some properties have to hold. For instance, both A and B have to create one particle states from the vacuum for this thing, or the transformation doesn't have to be too singular. And there have been analyses of sort of other transformations you can make which violate the equivalence theorem in some way, but not this one. So the Maxwell transformation in 4 dimensions actually does, the equivalence theorem should hold. So, and the reason, of course, that amplitudes are the same is that when you take these correlation functions and you do a LZ reduction, which basically hits, you have to multiply them by powers of the Onshel momenta before taking them to 0, then you expect to get the same answers for the actual S matrix elements. Now, there's a small subtlety, and this was analyzed by a group shared between Durham and Southampton, which is that actually I lied a bit about saying that all amplitudes are 0 in self-dual Yang-Mills. There's a small exception, which is the 3-point vertex, which at 3 level, which is non-zero if you're in complex momenta or if you're in different signatures than Minkowski space. In Minkowski space, it is actually 0 in 3+1 signature because of the particular kinematics of Minkowski space. But in other signatures, you can have this. And they found actually that for this particular case, because again of 3-point kinematics, and if you go to different signatures, the equivalence theorem is violated, and you recover this vertex using this. So something didn't. So the Maxwell transformation technically should not be applied naively, and if you do it more carefully, then you recover the vertex. But more importantly than this, what we have to do is that we need to put a suitable regularization on our action before even doing the Maxwell transformation. And the way you know this is that if one tries naively in Yang-Mills theory or self-dual Yang-Mills to calculate this one loop amplitude, the immediate answer is 0. One really has to regularize first because it's a rational term and it actually arises an epsilon over epsilon effect in the Maxwell regularization. So, and one nice calculation of this was done by the Queen Mary group in 2006. So it's kind of clear that regularization plays a big role in deriving this amplitude. And the approach of this group, which was work done parallel to our work, is to use dimensional regularization. So combined with this 3-point vertex that they have and choosing dimensional regularization and doing the Maxwell transformation after you've done dimensional regularization, then they managed to recover this all plus amplitude. In our case, we did something different. We thought, well, this Maxwell transformation is something very nice in 4 dimensions because it is related to sort of the integrability of self-dual Yang-Mills, which is only true in 4 dimensions. So going to D dimensions somehow spoils the nice properties. So we wanted to actually stay in 4. And okay, now I'm going to sort of change, open a parenthesis for a little bit, because I'm going to start by explaining the motivation, what motivated us to use the particular regularization we're going to use. So this is all I think, as I've explained, a matter of choosing the right regulator to recover the amplitude. And how does this regularization scheme combine with the Mansfield transformation to give you the amplitudes that we're missing if you do it naively? So our inspiration was from something kind of very different, which is the Lightcone wall seat approach, which is an approach to gauge signal duality, a different approach to gauge signal duality, initiated by Bardacci and Thorne, but really something that Charles Thorne has been looking at for many, many years, and with various collaborators. And the idea here is to improve as much as possible on the early models of the 70s, on thinking of the wall seat as made up of large planar diagrams, and try to make this a bit more precise. And in particular, what they were doing. So, okay, obviously I cannot sort of really give a good explanation of sort of all their motivations and so on, and I can't do justice to their approach. But very roughly, if this is the coupling, 12th coupling, and everything is done in the planar limit, somehow you expect that in this sort of double scaling limit, this is the original expectation of the 70s, you're going to get very big planar diagrams, which somehow will map to a continuum wall seat of a string. That was the original idea. Now, at 't Hooft want to sort of turn this upside down and start from here, close to lambda equals 0. And they want to say, well, let's map just an arbitrary planar diagram. So we know how to calculate this planar diagram at zero coupling or close to zero coupling. So can we map it to a particular wall seat configuration? And in this wall seat, this is Lightcone. They use a Lightcone approach like we do. So this would be P plus, this would be X minus. I'm not going to give many details, but I can talk about this later if you want. So this starts looking like Lightcone string theory, but it's not. They really want to do field theory, but in string theory-like language. So in particular, this diagram here would be represented, as usually in Lightcone string theory, by this kind of geometry, which really describes the fundamental sort of geometry of X minus and a P plus, where the wall seat is lying on. So you've gauge fixed the wall seat here. And on this field, you want to have two scalars. Okay, so this is a momentum string, a momentum space string that you have. So there are two scalars living on the wall seat. It's a four-dimensional string. And you want to write a theory, more or less a string theory, path integral that gives you this answer. And then the idea is, well, okay, if you want to have more loops here, then you'll have to add more slits. And then they have to find ways of, maybe it's easier to sum up planar diagrams in this way, and eventually find out how to go to strong coupling. But it's still very early. It's still at the level of taking one loop calculations that we know how to do, and doing them in a more or less string theory language. So anyway, this might not make too much sense, but I'll come back to. I can explain privately also, sort of more details about their approach. But as far as we're concerned, we don't really care about that motivation. What we care about is that in order to make this work, they had to understand how to do Lightcone gauge theory computations in a way which is wall seat friendly. Now, wall seat friendly means, in their approach, that, well, for instance, first of all, see that there's a very clear distinction between these two coordinates, the transverse coordinates, and the P plus coordinate, which is the sort of the other longitudinal, say, Lightcone coordinate. So it makes much more sense to them to do things in a way which preserves this distinction. While if we were just doing field theory on the Lightcone, we would probably want to treat these three coordinates in a similar way. So that's one thing. So basically, when they want to regularize here, they're going to use a very different regulator for sort of these coordinates. Essentially, they discretize the wall sheet, that's their regulator, and a very different regulator for these coordinates. And I'll be focusing on the regulator they need to use for these. And another aspect of being wall sheet friendly is that everything that you write down in the process of calculating sort of loop diagrams, for instance, you want to put counterterms for renormalization. Everything has to have a local interpretation on this wall sheet that they've defined. So they have to make sure that all the terms that you need to add to Yang-Mills theory to have it make sense at the loop level actually have a nice wall sheet interpretation. So here are the main features of this approach, which we're basically following this paper by these authors. They want to do a normal Lightcone field theory calculation, so they're not really doing string theory, they're doing field theory. But they have these two main differences. one of them is that they want to use this, they need to use this dual momentum representation. So if you take a planar graph, you can always map from a picture where you're labeling the loop integral and so on by the momenta of particles, and you can always map to the dual momenta, which label the regions. And this is already done by Ed Hooft in his '74 paper. So the relation between the actual line momenta and these regional momenta is given by this. And for those of you who are familiar with the Alda-Maldacena work, I mean, these are exactly the same coordinates that they are using also. So I'm not sure what the real connection is, but this is definitely more friendly in terms of sort of trying to do this string theory approach, because line momenta, the regional momenta are actually what are labeling the boundaries on this wall sheet. So rather than giving momentum to these areas, you want to put things on the boundary, and that's sort of the reason that Thorne and collaborators are using. So that's one thing. And the other thing is that they need to regulate, because these amplitudes have infrared and UV divergences, and in particular for UV divergences, they choose to put this exponential regulator in the theory. Now, this looks very perverse from a field theory point of view, and one of the main problems is, of course, that Q here is just the two transverse directions. As I was saying before, there's a very clear separation of this approach between the two transverse directions and the other two that you've fixed to be the dimensions of the wall sheet. So this is something that a field theorist wouldn't do if you were thinking in terms of pure field theory. So it looks like an exponential cutoff, but it actually affects only two transverse directions. And it breaks several of the symmetries that you want to have. So it breaks more Lorentz symmetry than you've already broken by going to LightCo. There used to be a shift symmetry of the regional momenta, which meant that you can shift all the regional momenta, and since the momenta are differences of the regional momenta, they would stay the same. But this breaks the symmetry. But despite all that, Thorne and collaborators go on and show that actually reproduces all the known results for gauge theory, for pure Yang-Mills theory at one loop. So for instance, and I'll focus on this, this is all I'm going to need, this calculation. For instance, you can calculate the helicity flipping gluon self-energy in light cone Yang-Mills. So you just have this vertex. I mean, this is the only vertex that you have in self-dual Yang-Mills. But in the context of full Yang-Mills, it's just one of the vertices. And after so you want to make this, do this calculation in this framework with this funny regulator gone and put in the path integral and so on. And the answer you get is non-zero. So you get this answer. Now, this is already really bad, because this is an amplitude for a single gluon to flip its helicity as it propagates. Remember, everything is outgoing here. So a positive helicity gluon just becomes a negative helicity gluon. And this violates Lorentz invariance. I mean, gauge invariance is hard to see here because you're in a completely gauge fixed light cone gauge. But obviously, if you violate gauge invariance, you also violate Lorentz invariance. So that's one of the problems, of course, with this term. Also, it depends explicitly on the regional momenta and not the line momenta of the particle, which is another unphysical thing that you don't want to have. So you need to repair this somehow. And the way CQT chose to repair this, well, it's the most obvious way, I guess, is to add a particular explicit three-level counterterm to the action. So you have to define it so that it explicitly cancel this counterterm. And if you're in self-dual Yang-Mills, then this is the only one you need. If you're in full Yang-Mills, there are a couple more, but a finite number of them, which you can estimate based on the divergence of diagrams. So we end up in a picture that, okay, if we believe this stuff and we want to follow for a while this Thorne approach using the light cone wall sheet, in self-dual Yang-Mills, the correct regularized action is not just this, but you need to add this extra counterterm. That's sort of the whole sort of thing I'm taking out of this approach, that if you want to properly regularize Yang-Mills theory, self-dual Yang-Mills theory in this approach, which is wall sheet friendly and sort of four dimensionals friendly in a sense, but not something that you would normally do, then you need to add this counterterm. So if you did what you would normally do, which is dimensional regularization, of course, nothing would happen. This amplitude would give you 0 in dimensional regularization, so there would not be any need for counterterms. So we're doing something kind of not very obvious from a field theory point of view, because most people are used to doing dimensional regularization because of all these nice features. Okay, and now the next step is to observe that this identity, this remarkable identity, actually holds. and this is, again, in self-Young mills, or you can think of it as a subsector of pure Young mills that calculate the all plus amplitude. So these are all the contributions you can have to the all plus amplitude at one loop. And the numbers here just label the different channels you can have, so I'm just simplifying a little bit. And this gives you actually 0. And the non-trivial thing is that this actually gives you 0 in the integrand of the loop, if you root the momenta appropriately. So we knew that it gives you 0. If you don't regularize, we knew that the integral of this will give you 0, because the amplitude is finite, and it arises as an epsilon over epsilon effect. So if you don't regularize in any way, then you'll just get 0 after you integrate. The non-trivial thing, this is actually 0 even at the level of the integrand, if you root momenta nicely. And this was observed first by, at least it was mentioned to CQT by Sv. Bern. Since all the contributions give you 0, then of course the question is how do you get the right answer, which is non-zero? And the answer in this regularization, if you were doing, in this regularization you have to, you cannot forget the counter terms. So these are the things that were explicitly made to cancel these bubble graphs. Because remember, these are the Lorentz violating self-energy bubble graphs that you were getting. So if you add these, which you should in the real theory, then the answer is just that, so given by these two terms. And this actually directly maps to the calculation using dimensional regularization, where these were 0 to begin with, so there were no counter terms, and you still have to calculate these integrals. So if you do this properly, then again you derive the result that, well, everything is fine, and these are this is the answer. And it gives you the right answer. For instance, one calculation is in this paper by Brad Huber, Spencer, Travaglini, in dimensional regularization.
So you don't need counter terms for the vertices?
Not for, you would, but they will not contribute to this amplitude, the all plus. So if you go to the single minus, then you would have to add counter terms.
Because the tree level vanishes?
No, because it's just a matter of helicity. So the vertex counter terms would have the form gamma plus plus minus. And you can see, you have to look at the graphs a little bit, but you can see that they would not contribute to this amplitude. They would not, so the helicities are wrong to contribute to this amplitude. So, but of course for the single minus or for any other case, you need to include a 3-point counter terms, yeah. Okay, and now if you look at this formula, which I've schematically drawn here, of course you can think that you realize that you can use associativity of addition, in a sense, to shift the parentheses. So, because as I mentioned in the beginning, this is also 0, because that's the Bern identity, which is kind of non-obvious, but you can actually calculate it and see that the integrands vanish. So this tells you that you can actually calculate the complete, at 4-point, the complete one-loop amplitude, just using tree diagrams, but with suitable counter insertions. So summing over all possible ways to put this counter term. And Thorne actually does this in this paper. They calculate it because it's in a sense maybe hard to believe, but they actually do it explicitly, and they calculate that you get the right answer just looking at these diagrams. So, and this is where we start. So far I've been talking about other people's work. So the final answer, the final result of all this is that if you regularize in this sort of Wall Street friendly way, then this one loop amplitude just comes from 3 levels of Euler mills plus this counter term Lagrangian. That's all you need to write down these things. So no loop level calculations of Euler mills. And the idea is, well, can this be combined with what I was talking about before, the Mansfield transformation? So what I'm going to do now is apply this Mansfield transformation to the self-Euler mills action, but regularized as Thorne would have it. So my full self-Euler mills action, regularized properly, has the kinetic terms, the interaction term, the self-Euler mills interaction term, plus this counter term. And then I'm going to do the Mansfield transformation, which, since I'm in self-Euler mills, just maps these two things to a kinetic term. And this will have to plug in the transformation here. So I'm still doing the original 4-dimensional Mansfield transformation. And I'm not going to do dimensions like the Southampton group would do. I'm just staying in 4. So, and why? Because this in full Young mills, so suppose I had also the vertices of full Young mills here, I would be guaranteed that I'm going to get the correct set of MHV vertices at 3 level. So I don't want to change that fact, which already works quite well. So all I want to do is change the loop structure. So now this term, of course, given that it comes from a limit of a string theory sort of approach, is not very nice as a field theory term. In particular, one has to, it's obviously non-local in many ways, First, it depends on the original momenta, because that's what the counter term you want to put depends on. Also, you have to associate different momenta to each of the lines of the gauge field in double line notation. So it's something that obviously is not very nice from, if you're looking at the gauge theory action or a gauge theory counter term. So it's a non-local term. But given that it originates as a string theory calculation, then we kind of accept it and see what happens. So you can take it, and then
So this counter term is correlated with this way of cutting off the Gaussian. Is that?
yes. So, but to figure this out, you have to actually do the calculation. So you have to do the bubble calculation. So this came from a bubble because you see it only has two. So it's a self-energy term, but you have to actually put in this exponential counter term and integrate out, and you see that at the very end, when you take the regulator to 0, so delta was this regulator. When you take it to 0, you get a finite answer, which I had before, but basically is given by this sum of regional momenta. And this is just a fancy way of putting it into, writing it as a Lagrangian, but the calculation, of course, is in terms of the amplitude. So the self-energy amplitude depends explicitly on these regional momenta, and not just on differences of regional momenta.
And again, you'd expect a bunch of other counter terms, because you don't need them.
Yeah, I don't need it. So there were no other counter terms in self-Tullio Mills. So here I'm focusing on self-Tullio Mills. So in self-Tullio Mills, it's easy to see that there's no other amplitude you can write down. There's no at one loop that has this behavior. So the vertex correction will not give you anything. There's no way to even write it down because everything has to be all plus there. So the only contribution in self-Tullio Mills is the one with the one coming from the bubble graph here, and that's because your vertices are like this. So you get this. This is the only contribution that will give you a Lorentz violating result, and the other one is where just the routing is different in the loop, but you don't get any other corrections. But if you go to Fullian Mills, of course, then you have another vertex and the quartic vertex also, and then you can create many more Lorentz violating sort of amplitudes, which you have to cancel by suitable counter term. But that's why I'm kind of focusing on self-Fullian Mills, which is kind of simple because this is the only problematic thing you have, which needs a counter term. So anyway, the precise form of that counter term action is not really important. The important thing is how to actually appear. I mean, that you want to reproduce the right Feynman rules for it to cancel all the bubbles in the original calculation. But you can see that, first of all, it depends only on AZ and not on the AZ bar. It was, well, from the form I had just in the previous transparency. So it's clear that if you transform it, then you will only need to transform A's to B's. There's no B bars in this game. And schematically, it was a 2-point counter term, so it had 2 A's. So when you do the mass transformation to B's, there are several ways of doing it. So you have to sum over all the possible orderings. So here is the case where it has become, so each of the A has split into 2 B's. And here the first A has become 3 B's, and the last one has just become a B, and so on. So these are all the ones you need for the 4-point calculation. Of course, for 5 points, you have to put all the ones that give you 5 B's and so on. Now, if you look at the expansion, which gave you, this is the mass field transformation essentially, which gives you A in terms of B. So you have to basically plug in these coefficients into the counter term I had on the previous page. And what you get, so this is pictorially what happens. So this 2-point counter term, there are several ways of creating 4 B's out of it. And these, one has to be careful, these are not propagators. This is the same vertex. So this is just a vertex. I'm just trying to demonstrate pictorially how which A becomes B and so on. The total contribution looks like something like this. So there are 6 terms. And the thing here, of course, which is not very nice, is that they depend, since the counter term depends on the regional momenta, these also depend on the regional momenta. So not on the actual momenta that you would like them to depend on. So you start with a formula like this, and you have to do some work and manipulate it using spinor identities, use momentum conservations, and various funny regional momentum identities that appear, but these are technical details. Then the result of it is that after you do all this, you can write this vertex, because remember now we're talking about a vertex that's in the Lagrangian. So we took this counter term, which was a vertex in Lagrangian, and we're mapping it to new terms in Lagrangian in terms of the new fields B. And you get something like this. And this is the non-result for the 4-point. So, and these are things that vanish on shell. So the vertex is not, so basically they give you the off-shell continuation of this thing. What we would claim would be the correct off-shell continuation of the all plus amplitude, which is as this, to become a fully off-shell vertex. There are some technical details, but I don't think I need to show them about the off-shell structure. One can repeat the same thing for the endpoint. So in this case, now you have still the same counter term, which is all you have, just a 2-point counter term. But each A can now sprout many Bs. So you take an arbitrary amount, and you have to sum up all possible permutations that give you the same final answer, the same final ordering of Bs. And you can rewrite this as a double sum. It's clear to see that you obtain a double sum if you do this, which still depends on the regional momentum. And the question that one would like to answer is whether this is actually equal to the known result, which is in this paper by, in a paper by Byrne, Dixon, Dunbar, and Kosover, which is this. So the difference here, this is a quadruple sum over actual momenta. Well, here we have regional momenta, and it's not really obviously clear that these two things are the same. Now, this is very similar to a conjecture that in another paper, Byrne, Dixon, and Dunbar, and Kosover had, which related MHV amplitudes, related the all plus amplitude in self-Euler Mills to MHV amplitudes in n equals 40 super EM Mills, but they were playing with dimensions and so on. There were some details here, but it also involved mapping something which starts off as a quadruple sum to something which is a double sum, because MHV amplitudes are a double sum. But anyway, the answer here is that we actually don't know yet. We don't have a precise proof that it maps to the endpoint answer. But what we have done is verify that this endpoint expression that we get has exactly the correct collinear unsoft behavior. So that means that collinear means basically that you take two adjacent momenta to become collinear, so they depend on the same momentum vector P, and the amplitude, if it has the right behavior, should factorize somehow like this, so this function should come out. And we can show that this is true for the endpoint case. Also, we can, another check that one has to do is the soft limits, where one of the particles, the momentum becomes 0. And again, it needs to split into this kind of function and some remainder part. And again, this is easy to show from the definition of our coefficients. So this endpoint conjecture, let's say, does have the right behavior to be the correct result. But we haven't actually shown that it is precisely equal to the quadruple sum that is the known result. OK, so I'm basically done. Some ongoing work. Of course, this was really for self-Euler Mills and for this particular amplitude within full Young Mills. So we would like to apply it to real full Young Mills, so to any kind of amplitude. In that case, as I was mentioning, we need to have many more counter terms. Well, not that many. I mean, basically, these are the lot. And for instance, just to give an idea, this gamma plus plus minus counter term that appears from a vertex correction looks like this. It also depends on the regional momenta, but linearly this time. So this presumably would also, when you transform it, will also give you something in some new term in the MHV Lagrangian. And to get the right answer for MHV, I mean, that's the conjecture because we haven't verified it yet, is that if you combine it properly with MHV vertices, 3-level, then this will give you the full set of one loop MHV diagrams for pure Young Mills. So that's one thing we're working on. And the idea, and one main difference from what you're doing from sort of the naive guess in this CSW paper is that we actually have many more. So their idea was to add one more vertex to the theory, this one loop, all plus vertex. But we actually see we have many more things. We have a conjecture for what the right off-shell extension of the all plus vertex is, but we also have things that come out from 3-point counter terms also. So there's many more new vertices that one has to add to the MHV, the 3-level MHV Lagrangian to get, we hope, the correct loop result. But the picture is still not very clear. I mean, some things become more technical if you go away from the all plus case. But the hope is still that one will set this up. Okay, so to conclude, we have an approach to obtaining the missing amplitudes in pure Young-Mills theory, missing in the naive sense that you cannot get them from MHV rules. So we think it's a step towards completing the MHV formalism at the quantum level. The main ingredients I used were the light cone. Everything was done on the light cone. I was using this Mansfield transformation, which stayed in 4 dimensions. I never had to go to D dimensions and redefine it in D dimensions. I used this very funny 4-dimensional regulator. I used, which led eventually to Lorentz violating counterterms. And it was these counterterms which finally gave us the right vertices and amplitude. So, and some outlook. So obviously, since this thing is not really something we know how to use very well, this kind of regulator, it would be nice if we could find a more quantum field theory friendly regulator which leads to the same results. But given that they were Lorentz violating and so on, it's not clear how, I mean, if you think of a normal QFT point of view, how you would get these kind of counterterms. But we're going to try, we're going to hope maybe to obtain the same kinds of vertices using, say, dimensional regularization. And this, I mentioned that there was another approach to calculating the same amplitudes by this group containing Paul Mansfield and Tim Morris and some students. So the relation is not very clear. I mean, their approach seems to be completely orthogonal from ours in that they use dimensional regularization. They're not really talking about a Lagrangian. They use cuts to reconstruct amplitude and so on. But it'd be nice to be able to relate this. Also, there's this twistor approach, which puts effective actions on twistor space and to calculate Young-Mills amplitudes. And so it would be interesting to see how our counterterms, or if they lift to 6 dimensions, and if they have any geometrical meaning on twistor space. And, well, of course, the main thing, and thinking ahead to sort of BDS conjectures and so on, is does this actually give us any insight at all on higher loop amplitudes? At least in the planar limit where all this applies, because nothing in this formalism can really easily be extended to non-planar. But you know, ideally, you know, if this formalism can be made to work and it's not too complicated, maybe there will be something to be said about iteration of amplitudes and so on at loop level, at multi-loop level. But this is really far in the future at the moment. So the general questions to come out here is of course, do these MHV rules that, okay, people have been using for supersymmetric theories and for other theories, do they actually mean anything more than just a trick to calculate some amplitudes quickly? Are there really a different theory which is equivalent to Young-Mills theory? And so there's 2 different questions. Are they consistent on their own? And even if they're consistent, are they equivalent to Young-Mills theory? So yeah, thanks. Thanks for your attention.
I have an additional point. So on top of being equivalent to Young-Mills, do you believe that they simplify somehow the problems, or is it complicated?
That's a good question.
Those simplify at tree level that we know, but
at the tree level they do simplify.
But more generally, do you think?
Yeah, that's the thing. Maybe they're not. The problem. Okay, there's also 2 problems within this. I mean, it could be that you get a simple enough answer, but you cannot even compare with other people's answers, because we're using a completely different scheme from everybody else. And how do you tell some experimentalist, I mean, if that's the goal, to actually tell some experimentalist, okay, this is your amplitude, define everything in MS bar and so on. How do you actually go from what we're doing to there? You need to build up lots of work and confidence to actually say these things. But we're not really there yet. I mean, I think this is more, from my point of view, it's a more conceptual step. I mean, does it actually make sense to treat this MHV Lagrangian as a full quantum field theory in its own right? And okay, it could be that for some processes it's actually simpler than Young-Mills theory. Like for instance here, one can calculate the endpoint all loop amplitude, the endpoint 1 loop amplitude very easily from this approach, just combinatoric. But in a normal field theory approach, it would take you actually much more work. So it does simplify some things, but it's not clear whether it remains to be seen.
Okay, well, let's thank Kostas again.